So let's start. Let's begin with the wonderful world of our friendly neighborhood alkanes, the reactions of alkanes. All right. Our general learning objectives is to describe selected chemical reactions of the alkanes and explain the steps involved in the mechanisms of free radical substitution. All right. So you can already see that this creating PowerPoints at 5 in the morning is not working out. Knows that is fixed, right? So explain the steps involved in the mechanism of free radical substitution, right? Oh, there are other objectives actually, that are in the PowerPoint. So we're gonna go through that. So the reactions of alkanes. So let's start with the general formula: CnH2n plus 2, right? That is general formula for all alkanes. Everything differs from that general formula, and everything can be condensed to that general formula, right? The reactions that we're going to be looking at are combustion, cracking, both types of cracking, by the way, thermal and catalytic, then halogenation through the reaction mechanism of free radical substitution. Then we'll head into steam reforming and catalytic reforming. Now, something very, very important. Never mix this up. Reactions versus reaction mechanisms. A reaction mechanism is a sequence of elementary steps by which a reaction occurs. But a reaction that occurs in two or more elementary steps is called a multi-step or a complex reaction. Alright? So we're looking at this general rule. That is what a reaction mechanism is. What we call the overall steps of this reaction is what we call, a reaction, right? Meaning that you have a reaction, for example, you're adding hydrogen to an alkene. That is called hydrogenation. That's the name of the reaction, right? But it occurs by a specific mechanism. So in this case, right, halogenation is not a reaction mechanism, and free radical substitution is not a reaction, right? So there's a difference between reaction and reaction mechanisms, and we're going to be looking at them a little bit more. All right. So let's go. Combustion. The combustion reaction is a reaction between a substance that reacts with oxygen gas. So it burns in air, specifically with oxygen present, to give varying variants, right, of carbon, right? It could be it could be solid carbon in the form of soot. It could be oxides of carbon, such as the secondary oxide or the primary oxide of carbon, which is carbon dioxide or carbon monoxide, depending on the type of combustion. And we normally get water as a byproduct as well, right? So combustion, alkanes can undergo complete combustion or incomplete combustion. It really doesn't matter, right? Before I continue, can anybody explain to me like which color flame is complete and which color flame is incomplete? Just see if you remember anything from CSAT.
I think I remember that the blue flames are complete since there's no like. Well, all right. Let me explain the yellow flame. So the yellow flame is incomplete because you can still see like soot coming off,
Hmm.
and that's an indication that some of the gases are not reacted. But
Okay.
nutty blues are
And with the blue flame, it's completely reactive. All right. So complete and incomplete combustion, thank you for that, right, occurs depending on the supply of oxygen, right? So if there's a lot of oxygen in excess, then we're gonna have complete combustion because there's enough oxygen to react everything. Oxygen is a limiting reagent, technically, right? And then with incomplete combustion, yeah, oxygen would be the limiting reagent. So if you don't have enough oxygen, then we can't react everything properly, and we're not gonna have the complete formation of dioxides, we're going to end up with monoxide, which are really, really toxic, right? And some soot, right? So let's have a look at this. The complete combustion in excess oxygen, alkanes will burn with complete combustion. The products of complete combustion are carbon dioxide and water. So as we can see from this general reaction here, everybody understand so far? Let's drop a one in the chat. If everything is fine, everything is cool, no issues at all. And if there's a question, you just ask the question. All right. So go ahead.
Alright, I'm coming, Grandma.
All right. So, not sure if she had a question, but when she comes back. All right, so complete combustion, that's it. All right, those are any more questions yet? So, incomplete combustion now, oxygen is at a limiting amount. Then, therefore, we're gonna have incomplete combustion rather, right? Producing carbon monoxide, which is very toxic, right? And some carbon, solid carbon, right, which is soot, right? So it's producing a sooty flame, a reddish flame, right? And sometimes when you burn flames like from like let me see, kerosene. I don't know if you guys had a kerosene lamp. I think every carbon household should have a kerosene lamp, by the way. But if you
Yes,
did
sir.
have it, wonderful. If you burn it, you're gonna see like black
Yes.
coming off of the tip of the flame. So that black, right, could be synonymous with the sooty flame. And if you burn things close to like a concrete wall or something or anything else surrounding a flame, you see it becomes black. So that is the carbon, that is the soot that we're talking about, right, for incomplete combustion. Majority of combustion tends to be incomplete. My phone fell. Right? But yeah, that's generally it. So we see some examples of reactions here when we limit the number of oxygen atoms that react, right, within this type of combustion for the combustion of methane, right? So we're seeing in one generally, right? So in one generally, we're gonna have carbon monoxide and water being produced. Yes, water will always be produced, by the way. It's just that the carbon substituents or the carbon products change, right? In one of them now we have oxygen, right? And then we have elemental carbon or carbon solid, right? Soot, right? And water being produced. So these things tend to be produced off of these combustion reactions. Now we have okay, let me just ask any other issues with this? Any issues with this at all? Let me check the chat. Any issues with this? Okay, let me see. I see a question. Hold on. I'm not seeing it properly. Let me rearrange. What was my question again? Um, I was asking if there are any issues with this. Right? So I'm not sure. I'm not seeing any questions in the chat. So guess that is it. That is it for combustion, right? That is it for combustion. Not a lot, right? We're also called towards the reaction of cracking, which you will look at way more in depthly in module 3, right? Cracking is the name given to breaking up larger hydrocarbon molecules, which are usually alkanes, right, into smaller, more useful bits, which are usually smaller alkanes and alkenes, right? So you have different types of cracking. You have thermal cracking that occurs based on the name at high temperatures, and catalytic cracking, which using a catalyst, right, we change the general activation energy of the reaction, or we change the pathway, right? So it really occurs at a lower temperature, right? And lower pressures as well because of the catalyst being present, right? And one thing to note about cracking, cracking isn't defined in a sense. The reactions aren't defined. So you can actually create any minor products and any major products you want, right, from cracking, right? So each and every single reaction can be unique for cracking, right? So I'm gonna exclaim on what that means, right? But first of all, we want to practice. Before we move on, I want you guys to complete writing the chemical equations to represent the cracking of the following hydrocarbons. Alright? So I'm going to give you guys 3 minutes to complete the cracking, 2 minutes actually, to complete the cracking of these hydrocarbons. Alright? So I'm just going to start now. 2 minutes. Just crack these up. Octodecane, nonane, and yeah. Just to be fair, I'm not going to be checking everything. I just want you to practice. And then we're gonna look at the cracking reaction to see if you guys made sense. All right? 'Cause if I check everything in, we're gonna take way much longer than anticipated. All right, guys have 1 minute left. Just finish up your reactions. Make sure that they're balanced because conservation of mass. All right, please remember that. Balance your things. Put in state symbols. And you guys should remember state symbols from CSET because the longer the chain, right, the stronger the bond, right? But generally here we can just put nonane and this, I think it's trideca, tridecane. You can put this as gas as well. And then the one with the 18 carbon, you can put as a liquid actually. All right. So 10 seconds, 2, 1. All right. So this is generally one of the things that we can look at, right? So looking at pentadecane, right, we have this type of cracking, not cranking, right? So it really doesn't matter how you slice it, really, right? You just know that you have the creation of alkanes and alkenes, right? So it really doesn't matter what products you come up with, doesn't matter. Just know that everything should be balanced and you must have an alkene and an alkene. If you don't have an alkene and an alkene, it is not balanced. Let me tell you that. It will not be balanced. All right. So that is generally what cracking is, right? So you destroy, well, wouldn't say destroy. You break up large chain alkanes into smaller alkenes and alkenes. That is what it is, right? So that is it. Any questions or concerns? Any questions? Okay, so I'm seeing in the chat. Okay, that's suitable. All right, I'm
Excuse
seeing
me,
suitable.
sir.
So go ahead.
Yes, sir. Yeah, excuse me, sir. How exactly do you know what it's going to be broken up into?
Exactly. We said that cracking is unique, right? It is really unique. There really isn't any single unique reaction specifically for cracking. So it's not that you know what it's going to create. You just know that there should be alkanes and alkenes, and as long as your reaction is balanced, you're fine. So everybody may have different substituents or different products, right? And those are all completely valid ways of cracking. Understood?
Oh, yes, sir.
Right. So that should be fine. Now, catalytic difference, right? So catalytic cracking now, um, modern cracking tends to use zeolites, right, as a catalyst, right? So they're aluminosilicates, right? They're really aluminosilicate complexes, right? You're gonna be looking at it a little bit more in depth in module 3 when you look at the alumin no, the crude oil industry, right? So you have this generally. You use zeolites, right, which are a type of catalyst that helps with the type of reactions that happen, right? So with catalytic cracking, since there's a presence of a catalyst there, you generally require around 500 degrees Celsius, around there moderately, right? And you have like low pressures. You don't require high pressures or high temperatures for catalytic cracking because a catalyst is present, right? So that's generally how it works, right? You don't have to get into the nitty gritty right now. That's module 3, right? Just know that this is catalytic cracking. The catalyst is zeolite, usually zeolite, which is an aluminosilicate complex, right? With the presence of a catalyst, catalytic cracking occurs at lower temperatures and moderately lower pressures. Full stop. That is what you need to know so far for this reaction, right? There's a summary at the end of the slide, by the way, that sums up everything. Right, so we have that there. Catalytic cracking. For thermal cracking, however, there is no catalyst. Therefore, we need some way to allow these molecules or allow this reaction to pass its activation energy. We need more energy itself. So the range of around 450 to around 750 degrees Celsius, thereabout, upwards of 70 atmospheres, high temperatures and pressures are required for thermal cracking because there is a lack of a catalyst. Now, as a chemistry unit 2 student, We are not only looking at organic chemistry for the sake of organic chemistry, but we're looking at it as industry professionals as well. Thermal cracking requires way more heat and pressure, therefore, it is much more expensive to do. Therefore, that's why we said here modern cracking, we tend to use catalytic cracking now, right? Because it's much more cheaper, right? It's more cheaper or it's more cheap than thermal cracking. Because thermal cracking, you have to take into consideration the billing expenses. Think about the fracking industries and the cracking industries and the petrol industries within your respective countries, right? Um, or if your country has that, right? Then you will have to understand the amount of different type of electrical plants that they have around these areas, right, to supply the electricity to increase the temperature within chambers for cracking to occur, right? But if they have zeolite or they use different types of catalysts, they don't require as much energy, right, to break. They don't require as much electricity. Therefore, it's going to be cheaper, all right? So catalytic cracking is much cheaper than thermal cracking. That's one thing man to maintain to know, all right? And they will ask stuff like that on paper too. You will be going through all of Unit 2 and realize that why are they asking me questions about economics? It is important, right? Halogenation of alkanes now. Alkanes, the most basic form of all organic compounds, undergo very few reactions, right? But one of the most notable reactions is halogenation, or the substitution of a single hydrogen on an alkane with a single halogen to form a haloalkane, right? This reaction is very important in organic chemistry and allows a wider, more broader spectrum of reactions to occur, right? The creation of haloalkanes allows for us to know in the future look at the reactions of haloalkanes, right? So halogenation now. Before we enter the entire debacle of halogenation, we want to recap the mechanism and electron movement that occurs within organic chemistry. Bonds break and bonds form. I know, right? Really crazy. But we have to really study how bonds break and how they form, right? If we have a covalent bond between two atoms, right, one of the atoms can remain, right, can remain in bonding with an electron, right, can keep an electron to bear a negative charge, and the other will bear a positive charge. Meaning that if we have something like this, using an example from there, right, if this molecule were to break, right, the chlorine is more electronegative or electropositive? Which one? Is the chlorine more electronegative? Yes or no?
Yes.
What is
Yes.
electronegativity?
Repeat.
What is electronegativity?
Its ability to pull the electrons to itself.
Wonderful, right? The tendency for a species to attract electrons. Wonderful. So electrons would be more strongly attached to chlorine because of the high electronegativity than hydrogen, right? So generally within this bond, you will see the movement, right, of electrons towards the chlorine. You will see something like this, right? Now I use a full head arrow to show that two electrons are moving. When you use full arrows, right, that show the movement of two electrons. Please remember that, right? So it shows the movement of two electrons, right? A pair of electrons, right? And what will occur is that you're going to end up with one species, that would be a proton, and you're going to end up with chloride. Make sense? Makes sense, right?
Yes, sir.
All right. Now, let's say that they have comparable electronegativities, such as in the dichloride molecule, right? Well, the dichlorine molecule, right? So we're gonna have this here. They have comparable electronegativities, so they won't cleave heterolytically, right? Which this is heterolytic cleavage, by the way. This is heterolytic. Forgot to write that down. Heterolytic. It's not writing properly, but yeah, heterolytic, right? Lytic to lyse means to cleave, which means to break, which means to cut, right? Hetero means that one gains all the electrons and the other remains deficient. Heterolytic, right? What if they're homolytic? Suppose both of them remain in having electrons, right? We're gonna have something like this. You're gonna use fish hook arrows or half arrows. Half arrows show the movement of one electron. So one electron goes to one of the chlorine and the other goes to the other chlorine. And we're going to end up with chlorine radicals. A free radical is an electrically neutral atom or a group of atoms that has one unpaired electron. It is really, really unstable and highly reactive, right? So that's what we're seeing here, denoted by the dots beside the chlorine. That is the chlorine radical. Radicals are really, really, really interesting, right? For persons who do keep food and nutrition, you'll know about radicals, right? And then you're gonna have stuff like antioxidants and stuff like that that you will consume, right? If you have a lot of free radicals within your system, free radicals can damage DNA, can damage cellular machinery, can kill, right? It's really reactive, so it's gonna react with almost anything around. So that's how we use antioxidants and stuff like that to try to reduce the radical formation and stuff like that, right? So we have free radicals there. Any questions on our concerns about homolytic or heterolytic fission? Any issues? Questions, concerns? Nothing? No. All right. So free radical substitution occurs within this general thing now. Before, okay, this is generally right. So free radical substitution reaction is a reaction that occurs by a free radical mechanism, right? That results in the substitution of one group for another. So we're going to have the formation of highly reactive free radicals, and this occurs through UV light, right? That is how we really displayed it in CSEC chemistry, right? And that is how we shall look at it in Cape chemistry. So if we look at something like this, right, we must have the interference of UV light, donate looking at it through the concept of let me see, let me make this smaller so I can write a little bit easier. All right, so the light, we use H nu to explain this, right? That looks like a gamma. Let me just write, it's not a V, it's a nu, right? Greek letter, right? So H nu, that is how we denote light or UV light in this case, right? That UV light will destabilize halides, right? Molecular halides, for them to react in such a way to give radicals, right? So therefore, if you're gonna need a free radical substitution to happen, you either need like radicals within the within the solution already, or you need light to activate or to initiate the reaction, and that's why we have the first step being initiation. All right. So first, the molecule initiates everything, right, by the creation of radicals. So initiation is stable species to radicals. That is what initiation is, right? And since free radicals are so reactive, they do create chain reactions, right? So this chain reaction allows for propagation, or we can see that through propagation, which is the second step of this mechanism, right? In which radicals created in initiation will now react with stable species, right? So in this case, we have A plus C and D. A is so reactive, it will actually pull C from D, right? So remember that it's one electron, and we show electron movement from the electron specifically. We don't show it from A. That is wrong. We do not show it from A. We show it from the electron specifically. That is important, right? And we do not show, well, let me just show the right one first. We show electron movement from the bond because electrons are in the bond, not from the species. That is wrong also. So you only draw arrows from electron locations to where the electron is going, right? So if I see you guys draw a mechanism that has something looking like it's coming from one species and not where the electron is, It is wrong. You may lose a mark, but I'm going to lose all the marks because I forgot to give you marks, right? So it's something like that. If you forget to draw the arrows from the correct areas, I will forget to give you marks. That is how I am. All right. So that is it. So that is how it works. And then we're gonna have the last electron within this bond going to D. And here we can see that A and C are now joined up, and we have a D radical. So in propagation, right, we have a stable species plus a radical gives a stable species and a radical, right? And this is important for summarizing and memorizing and stuff, right? So that's what's happening there, and there are multiple propagation steps, right? So once the radical creates another radical by reacting with a stable species, that will then go on and on and on and on, and propagation goes on and on and on, right? But we generally just summarize it, right? Termination now. Let's say that two radicals meet up, so F radical and G radical from the diagram here, right? F donates its electrons and G donates electrons, right? These electrons meet up. It's going to create Fg. And then if all reactive species, all the radicals meet up in this way, meet up with other radicals and create stable species, then unless you're continuing to supply UV light, the reaction is finished, right? Because there are no more radicals to react. The only way you can continue the reaction is to apply more light, right? So in this case now, when radicals react to give stable species, that is a termination of the chain reaction. That is a termination step. Are there any questions?
No, sir.
All right, let's look at it. Initiation, radical formed from a neutral molecule. Homolytic cleavage. Beautiful. H nu, indicating that there's some type of light or heat energy or something creating this radical, right? This pair of radicals rather. Then we have propagation. A radical generates another by reacting with a neutral molecule. So the radical generates another by reacting with a neutral molecule. We see a chlorine radical reacting with methane, right? Note where the arrows are and know what type of arrows they are. They are Fission arrows or half arrows. Therefore, it's only one electron the arrow signify the movement of. And realize where the arrows are coming from. That is coming from the electron and not the chlorine itself. These are coming from the bond and not the hydrogen or carbon themselves. Right? And it reacts to give a stable species and the radical. And abstraction tends to occur. Abstraction is the removal of a hydrogen. Right? That is what we call it. But you don't have to use the term abstraction. It's fine. It's cool. Right? You also have the creation of another propagation step. Right? We're showcasing this radical reacting to produce chlorine radicals or chlorine radicals. So this radical can now react with another halogen, right? To create another type of radical. So here we have a mono-substituted monochloro methane, right? So you can see it through this. H, 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 and you have your Cl, monochloromethane, right? So I think you should be able to see that. All right, propagation. Then you have termination steps. Radicals react with radicals to give stable molecules. So there are many ways in which they can be terminated. We could have a chlorine radical reacting with a methyl radical to give monochloromethane. You could have a methane radical reacting with a methane radical to give ethane. We could have a chloride radical reacting with a chloromethyl radical, right, to give dichloromethane, and you could have the same thing to give trichloromethane, right? Or in this case, this is not trichloromethane, by the way. Um, if you want to draw this structurally to see how it works, this is the molecule that you see here. Um, That should be a carbon. This is the molecule that you see here. This is this molecule. Hydrogen, chlorine, fluorine. Can somebody name this? Name that molecule, please. This molecule that we see here. Somebody name it, please. Just name it. I'll look at the name in the chat when it's named, right? So radical reactions usually provide mixture of products. Products mix can be identified by mole ratio. So if you have way more alkane than halide, then you're going to get mainly a substituted, a monosubstituted one, right? Because there's not a lot of chlorine radicals to go around to create fully substituted alkyl species, right? There's not enough to create chloroform, right? This is chloroform, or what we call tetrachloromethane, right? The same chloroform that people put on cloths and cover your nose with in movies and they drop us, whatever, right? You knock out. That is what chloroform is, right? It tends to have that effect on people, right? Or if you have way more halide, right, or halogen than your alkyl species, then you're going to have, the creation of that fully substituted species, right? So this is how free radical substitution works. I'm not seeing the name in the chat, I'm not seeing the name. All right. But go ahead. Are there any questions? Any concerns? Any emotional outbursts? Any issues? If you're listening, please drop a one in the chat, right, to indicate that you're good and that you're ready to move on. Pentachloroethane. What a wonderful answer. Right? It's fine. So you have one, two, three. Let's see if we can try to name this now. One, two, three. We have try there, right? So we have three of them there. So you could have like this is the first carbon. I will give you stability, and then this is secondary stability. Priority. I mean, all right. Having a look at this. One, two, three. One, one, one. All right, and then you could have two, two. It's gonna be a weird structure if you use IUPAC standards. But yeah, that is fine. It's a pentachloroethane though. All right. So let's just move on. Don't wanna waste a lot of time. Steam formation is another reaction that we can look at. So steam formation is what we use to really create hydrogen gas and stuff like that. Hydrogen is important because you can use hydrogen as an energy source opposed to general fuel sources, but there are issues, right? Um, give me a few more minutes. We should be done in a few more minutes, right? But there are a few minutes. There are a few issues with hydrogen production, and I think you should, as chemists or as scientists, look at hydrogen production and the issues with using hydrogen as energy sources, right? But looking at this now, steam formation, light hydrocarbon reacts with steam, right, in the presence of a nickel catalyst, right, to produce carbon monoxide and hydrogen, or you have carbon dioxide and hydrogen. So if you have excess water, you have carbon dioxide being produced. If you have limited water, you have carbon monoxide being produced. That is steam reformation, right? So steam reforming, right? So that is generally it. You can also have steam reformation to change aliphatic, straight chain carbon compounds into bond cyclic compounds, right? So there's also something like that. You can create toluene from alkenes and stuff like that when you look at steam reforming larger chain carbons, right? So that's generally it. So just to summarize, the combustion of alkanes results in the production of carbon dioxide and water, right? That would be what type of combustion, by the way? Which type of combustion gives you carbon dioxide and water?
Complete.
Wonderful. And what does incomplete give us?
Carbon monoxide.
Right? Or it can give us soot as well, right? Okay. But it must give us water because that's combustion. Cracking involves thermal decomposition of alkanes, leading to the formation of shorter chain alkanes and alkenes. And we know that we have two types of cracking. What are they?
Catalytic and thermal.
Catalytic and thermal, lovely. Right. Why is catalytic more favorable than thermal?
Because thermal requires like factory equipment and so on. That's much more expensive than the catalyst.
Right. It's much more expensive to do it through to raw energy through thermal decomposition, right, by itself because it requires way more money to supply enough energy and electricity to increase those temperatures. While it could just put a catalyst and allow the activation energy to chill out a bit to lower the activation energy, right? So it requires less electricity or energy to really increase the temperature. All right. So substitution reactions entails the exchanging of one atom or group with another. All right. So that's what we're seeing. We're exchanging hydrogen on an alkane for a halogen. All right. And bonds break in two ways: homolytic fission and heterolytic fission. Can somebody tell me what heterolytic fission entails? This is the last. Well, no. What
Can you
does
repeat the
go ahead?
question?
What does heterolytic fission entail?
So heterolytic fission is when a bond breaks and both electrons go to one atom. The atom that is more electronegative.
Wonderful. Right? Because I was about to grill you about that, by the way. Homolytic fission. Who would like to take that one? Homolytic. No? Nobody? Go
So
ahead.
homolytic fission is when the bond breaks and both atoms receives one electron, and it's
Wonderful.
normally represented by a fission.
And what happens? What is the result of homolytic fission?
It creates radicals.
Wonderful. Shanice, what are radicals? Is Shanice aware? Is she lucid? Is she awake? Okay, if Shanice doesn't respond, Karjina, what are radicals? Go ahead, Karjina.
I know how to identify it, I don't know how to explain it.
You know what to explain? All right, who can help out, Karjina? Go ahead. I heard that. Go ahead.
Atoms are groups of atoms with unpaired electrons.
That
Yes, that are
are highly
highly.
reactive.
Eh, okay.
Highly reactive. Wonderful. Right? They're neutral as well. So neutral and highly reactive atoms with unpaired electrons. Right? So we have that there. And the lasting reaction mechanisms represent the movement of an electron pair with a curved arrow. Always curved, right? But if you have a full arrowhead, then that is a pair. Wonderful, right? And then the fishhook arrow is the single electron. Right? But that is it generally. That is the summary of that. Right? We just have catalytic reforming to look at. As you can see, creating sites 5 o'clock in the morning is not good. Because why did summer come before catalytic reforming? Right? So let me just put that there. Right? Uh-huh. All right. Catalytic reforming, really, really simple. This was the one with toluene with the creation of um arenes, right? So with longer chain hydrocarbons, you can create arenes and hydrogen with catalytic reforming, which guess what? It uses a catalyst, right? A platinum catalyst is generally used, right? But that is that. That is that really. Right. This is the last thing I really want you guys to look at. So if you want to attempt it, please attempt it. Right. So let me see what you can do with this. Right. The overall equation for the reaction between butane and chlorine, also methane and bromine. Right. And give me the reaction mechanisms. Right. That means I want to see the name of the reaction, then the mechanism, then initiation, propagation, and termination, right? And then you write an equation to show the cracking of hexane to give three different hydrocarbons, right? But this, you guys can send these answers in my inbox if you want to attempt them. I do recommend that you screenshot right now. Just give you 5 seconds. Five, four, three, two, one. All right. And then you just attempt them. All right. Just let me know what the answers are in the comment section or in the group or whatever. All right. So we have that. That is the end. That is our reactions of alkanes. Wonderful, isn't it? I know. I know you guys are just bubbling with excitement and energy at the moment.